Hello, this is a small demonstration on analog amplitude modulation using three types of equipment: a signal generator, a spectrum analyzer, and a digital oscilloscope. First of all, we are going to describe the functions of the signal generator, which will generate the amplitude modulated signal. In this signal generator, we can establish different parameters such as the frequency of the carrier signal, the amplitude or the power of the transmitted signal in this case, and then here on the menu on the left we can set up the different parameters of the amplitude modulation. The relevant ones for this demonstration are the amplitude depth in here, that sometimes is known as modulation index, the frequency of the information signal or modulating signal, and the type of signal used as an information signal or modulating signal, in this case a sine signal. The frequency of the sine has been set up at 50 kHz. This particular signal generator generates a double sideband large carrier amplitude modulated signal, which means that the transmitted signal has the two sidebands together with the carrier transmitted. First of all, we are going to observe the transmitted signal in the frequency domain looking at the screen of the spectrum analyzer. The spectrum analyzer setup has been done by selecting or choosing the center frequency at 10 MHz, being this frequency the same as the carrier signal, and a span of 200 kHz. As we can see in the screen, the carrier signal appears exactly centered at 10 MHz, and the two sidebands corresponding to the amplitude modulated signal at both sides of the carrier frequency. Because the information signal was chosen to be a sinusoid of 50 kHz frequency, those two sidebands appear exactly at a distance of 50 kHz from the carrier frequency. We can see this here in the numbers indicating the position of the two delta markers with respect of the center marker situated in the peak of the carrier. For this particular signal generator, the information signal or the sine wave that we are using as a modulating signal has a maximum frequency of 50 kHz, which is the one that we have just selected. So the only thing we can do is decreasing that frequency, but that is good or enough to demonstrate the concept that when we decrease that frequency, we can see how those sidebands get closer and closer to the carrier frequency because of the frequency of our information sinusoid has been decreased. If we start increasing that frequency back up to 50 kHz, we see how the two sidebands spread away again from the carrier frequency. Now we will look at the effect of varying the modulation index over the spectrum of our transmitted signal. The modulation index indicates the coefficient or relation between the power of the information signal versus the power of the total signal transmitted. The higher the modulation index, the more similar the power of the information signal will be to the power of the total signal. Right now, we have a modulation index of 10% chosen. If we just go down to 0%, we see how the modulated signal disappears and we only have the carrier signal. Why? Because 0 modulation index is equal to no modulation. On the other hand, if we start increasing the modulation index in 10% steps, being this 10%, 20%, 30%, 14%, and so on, we can see how the power of the information signal with respect of the carrier keeps increasing until it reaches its maximum for 100% value of the modulation index. What we are seeing in the screen right now is an amplitude modulated signal where the information signal is a sinusoid at a frequency of 10 kHz and with a modulation index of 50%. Before we move into what the modulation index does to the time representation of the signal, let's look at the representation we have at the moment. As we know, for amplitude modulation large carrier, the signal information is embedded in the envelope of the transmitted signal. As we can see here, the information sinusoid is perfectly embedded in this envelope. If we change the type of information signal to, for example, a triangular signal, like this, we can see how the triangular signal is perfectly embedded in the envelope. Again, the same can be seen if we change the information signal into a square signal, or if we change the information signal into a ramp signal. In order to study the effect of the modulation index in the time domain representation of the signal, we go back to the case where our information signal is a sinusoid. The modulation index is going to determine the difference between the maximum and the minimum values of the signal envelope. Right now we have a modulation index equal to 50%. We can see how when we decrease this modulation index, now 40%, 30%, 20%, the difference between the maximum and the minimum of the modulated signal decrease. On the other way, when we start increasing the modulation index, 70, 80%, 90%, up to 100%, is when the maximum difference between the envelope of the transmitted signal and the minimum of the envelope of the transmitted signal is achieved. We have to remember that for amplitude modulation double sideband large carrier, in order to employ an envelope detector receiver type, our modulation index cannot be more than 100%. If this modulation index goes over 100%, we will not be able to extract the information signal from the envelope